This is a presentation of the paper Radio Localization and Sensing Part 2, State of the Art and Challenges. My name is Wymeersch. I'm at Chalmers University of Technology, and this work was performed in collaboration with my colleague Gonzalo Seco-Granados from UAB in Spain. This presentation summarizes the paper from IEEE Communications Letters on Radio Localization and Sensing Part 2. You can find the video of the first part on YouTube, and I recommend you watch this first before watching this video. This is the outline of this presentation. I will first introduce the advances envisioned towards 6G for localization and sensing. Then I will talk about advances in channel modeling, then how to improve coverage and identifiability, then how to improve accuracy, and then I provide a more in-depth outlook towards 6G. So let's start with the introduction and why we would need 6G for localization and sensing. This figure shows on the x-axis different levels of location uncertainty, ranging from 1 centimeter to 100 meters. On the y-axis, we see different deployment environments, including indoors, urban outdoors, and rural outdoors. The vertical lines represent different use cases, ranging on the right from emergency call localization with very loose location uncertainty requirements, all the way to the left where you have cooperating robots and extended reality, which have very stringent localization requirements. The ones that are more stringent correspond to some of the typical 6G use cases. The different blobs represent different radio technologies. We see in light blue GNSS, including GPS, Galileo, Baidu, and so forth, which in principle could cover most of the use cases, but works only in rural outdoor scenarios where you have line of sight to a sufficient number of satellites. There's a blob for 4G, which can provide accuracies on the order of 10 meters, 5G going down to 1 meter, ultra-wideband going down to 10 centimeter, and finally, there's the vision for 6G to provide accuracies on the order of 1 centimeter in indoors and urban outdoors environments. And today we will talk about some of the advances that are being considered to make this happen. Let us look at the enablers going from 4G to 5G to 6G and how they impact localization and sensing. First of all, there's the communication requirement for higher data rates. The only way to get higher data rates is by having larger bandwidths, typically on the order of several hundred megahertz and maybe even several gigahertz. As we've seen in part 1, larger bandwidth leads to better delay resolution, so a better ability to resolve multipath in the delay domain. These large bandwidths are not available at sub-6 gigahertz frequencies, so we need to move to higher carriers, including millimeter wave frequencies and sub-terahertz bands. At these bands, the channel is more benign and behaves more geometrically. And this is of course good for localization and sensing because this allows us to interpret fewer multipath components in a geometric manner. Now when we go to these higher frequencies, we will need more antenna elements in order to overcome the path loss. For a fixed area, so a fixed number of square centimeters, we can put more antenna elements at higher frequencies. When we have more antenna elements, we basically improve the angle resolution. So this is the ability to resolve multipath in the angle domain. Of course, all of these benefits, they don't come for free. So there's no free lunch. When we go to higher carrier frequencies, we'll have reduced coverage because of path loss. We will have more impact of hardware impairments, as we will see soon. And also there's an increased power consumption. In combination with these enablers, there's also several advances towards localization and sensing. Here I will list just 4 of them, but we'll talk about more later in the presentation. First of all, there's the integration of sensing and communication, so-called ISAC, which means that we will have 2 functions with 1 system. Secondly, there's the use of reconfigurable intelligent surfaces, which create artificial multipath components that can be useful for communication, but also, as we will see, for localization. There are new MIMO technologies, such as extra-large MIMO and cell-free MIMO. And finally, there are advances in algorithms and designs, including data-driven or AI-based, but also model-based methods. The way that this paper is structured and also this presentation is we will first talk about modeling, talking about new channel models that include effects such as near field, non-stationarity, and wideband effects, as well as the importance of hardware impairments. And then we will talk about how we can improve performance. First of all, in terms of coverage and identifiability through multipath exploitation and creation, where the creation will be done with reconfigurable intelligent surfaces. And finally, we will talk about how we can improve accuracy through more smart signal design, by using carrier phase information, and by tracking users or objects over time. Let's first look at the advances in channel modeling. This slide recalls the channel model from the previous presentation, part 1. We have a transmitter, in this case a base station, a user, and a multipath channel. The multipath channel at a certain subcarrier or a certain frequency at a certain time k is a matrix if the transmitter and the receiver have multiple antennas. This matrix is a superposition of L paths. Each path has a complex channel gain. With each path, there's also an array steering vector at the user side, which takes as argument the angle of arrival. This angle of arrival can have an azimuth and an elevation component if the user has a planar array. For each path, there's also a transmit steering vector, which has as argument the angle of departure at the base station, again in azimuth and elevation. Then we have a phase progression across the subcarriers, which depend on the subcarrier spacing delta f, as well as the delay of the path. And finally, we have a progression across time k, which depends on the Doppler of the path. So this is just a model that we've seen in the previous presentation. If we look a little bit more detail how these array steering vectors look like, so let's suppose we look at the receiver side steering vector and look at the peak entry in this vector. And this is an exponential, which depends on the position of the peak element at the receiver side minus a reference element at the receiver side, and this is shown at the figure on the right here. So there's a reference element at the receiver, this is called the phase center, and then an arbitrary element at the receiver, transposed with unit directional vector. And this unit directional vector is just a vector pointing from the reference element at the receiver towards the signal source. In this case, this would be some incidence point of a multipath component. This is a unit vector pointing towards the signal source. And this unit vector is identical for each of the elements in the array. And then you multiply with 2 pi over lambda. This is the standard far field steering vector, which depends on this angle of arrival, theta L. Now there are several extensions to this model. The first one is to account for wavefront curvature or near-field effects. This is visualized here on the right. So as you see, when the signal source, in this case user device, is close to the receiver array, then the directions from each of the array elements are different. And this is captured by this updated steering vector expression. So the steering vector expression now doesn't depend just on the angle of arrival, but directly on the position of the signal source. And the expression is just given by these differences of distances from the signal source towards the peak element with respect to the signal source to the reference element. It is easy to show that when the distance between the signal source and the array increases, we recover the standard far field model from the previous slide. So this is the first advance, where the steering vector depends on position, not just on angle. The second advance is non-stationarity of the channel. This means that different elements of the array will see a different complex channel gain. The easiest way to visualize this is by having a blockage. So if some of the elements are blocked, then of course the channel gain for those elements will be much smaller than an element that is not blocked. So if I go back to the previous slide, this means that this alpha L is not common for all of the elements on the array. This again makes the model more complicated. A third effect is the beam squint effect. If we look at the array steering vector here on top, we see lambda. lambda corresponds to a certain frequency, typically the carrier frequency. When the bandwidth is really, really large, then the carrier frequency at one side of the bandwidth, for instance, the lowest subcarrier, could be significantly different from the wavelength at the highest frequency. And this leads to a beam squint effect. This means when we have an intended beam generated in some direction, measured at the carrier frequency, and then we evaluate this beam at another frequency, the beam could point in a different direction. This is known as beam squint or beam split. A fourth advance in channel modeling is when we consider irregular spacing. When the elements of the array are not spaced exactly lambda over 2 apart, but are rather a different separation, larger than lambda over 2, or have an irregular spacing, we will have so-called grating lobes. Grating lobes look somewhat similar as we would have here in the beam squint picture. So there's a beam in an intended direction, but there can also be a so-called grating lobe, or a kind of ghost beam in a different unintended direction. All of these effects must be accounted for when developing positioning and sensing towards 6G. And this imposes new challenges for algorithm design. The next modeling advance relates to hardware impairments. The figure here shows on the left side the transmitter, in this case a user, on the right side the receiver, in this case a base station. If the user wants to send data across subcarriers, it will go through a number of steps. So it first goes to digital steps, including IFFT, cyclic prefix addition, and so forth. But at some point you go to the analog domain. You go from digital to analog. Then you have the mixing with the local oscillator. You have the splitting and you apply the precoding. Then there are power amplifiers, and then you go over the antennas. In between you have the actual propagation channel. Then at the receiver side you have again the antennas, low noise amplifiers, combining, mixing with the local oscillator, and then again analog to digital conversion, and then you apply your FFT to get your data. From a communication perspective, you care about what happens in the digital domain. So the red box here is the kind of end-to-end channel seen by communication. And as long as you can estimate this end-to-end channel, you can communicate. Now, within this end-to-end channel, there are several impairments. So there's phase noise, carrier frequency offsets, mutual coupling, power amplifier nonlinearity, and so forth. For the communication perspective, if you can estimate all of those impairments through the end-to-end channel, you don't care about them. However, for localization and sensing, you care about the geometric parameters inside of the channel here, the channel HI. And this means that you are very sensitive to all of those hardware impairments. So in summary, while hardware impairments are detrimental for communication, they are much more severe for localization and sensing, which means that we probably need more sophisticated calibration and estimation methods. Let us now consider a use case or a case study at 28 GHz with 400 MHz bandwidth, 64 antennas, and a transmitter at 2.8 meters away from the receiver. The figure on the left shows the impact of narrowband and wideband effect, so the beam squint effect. In this case, what we show is the normalized response, G of theta, of the considering a combiner W applied to the steering vector as a function of the angle of arrival theta. So the angle of arrival is shown here on the x-axis, and the response G normalized is shown on the y-axis. When we have a narrowband system, then the steering vector does not depend on the frequency. So the frequency dependence is gone, and then we have the curve shown in black. So the black curve is the narrowband normalized response for a combiner W listening to some direction here. Now when we apply the same combiner W, but the system is a wideband system, so the steering vector depends on the carrier frequency through the wavelength, then also the normalized response will depend on the carrier frequency. And that's what we show here in red for the lowest carrier frequency, and in blue for the highest carrier frequency, and in purple for the center, so the actual carrier frequency. So we see that for the carrier frequency in purple, the beam is not modified, but for the lowest frequency, the beam is shifted a bit to the right, and for the highest frequency, the beam is shifted a little bit to the left. So this shows the effect of beam squint, which is the dependence of the steering vector on the carrier frequency when we apply a combiner that does not depend on the carrier frequency. Of course, if we can design W to depend on the carrier frequency, this will be a wideband precoder, which we can implement with time delay beamforming. Then we obtain the purple curve again. So the beam is not perturbed and is pointing in the same direction for all of the frequencies. The last curve shown in red is the impact of hardware impairments through irregular element spacing. So in this case, the elements in the steering vector are not spaced exactly λ/2 apart, but are slightly perturbed. In this case, you see that the beam response itself is also perturbed. The figure on the right shows the far field and near field effect. So suppose that we apply a far field combiner, which is listening to some angle theta. And then we plot the corresponding normalized response, and in this case we consider narrowband system, so there's no beam squint effect. What we would have as a function of the distance to the array is that the far field response would be flat, because there is no distance dependent in the steering vector. This means that all users or all transmitters on the same angle away from the receiver would have the same normalized response. If we now apply the same far field combiner, but the system is in near field, then the response would be shown in red. So this means that transmitters very far away would have a high normalized response, while transmitters closer to the receiver would have a very low normalized response. So there's a mismatch. On the other hand, if we design a near field combiner, which is listening to a certain position, x, then we would have the curve shown in blue. So in this case, x is at about, let's say, 2.8 meters away from the receiver. The receiver applies this combiner W and F, and in that case, the gain would be highest for that receiver and would be lower for transmitters closer to the receiver and for transmitters further away. So there's a local peak, and this is known also as spatial focusing. Of course, the argument here was for combining. The same argument holds for precoding. So you could design precoders that are illuminating a certain distance, but have lower gain closer and lower gain further away. This is very different from a near field precoder, which would have a flat gain for all distances along the same direction. Let's now look how we can improve coverage and identifiability. The first method is to do so-called multipath exploitation. This is shown here on the right, where there's a transmitting base station, user acting as a receiver, and then there are different objects in the environment, in this case buildings. With each of the resolved multipath components, there are 3 degrees of freedom related to the unknown incidence point. So there's a 3D unknown for each multipath component. On the other hand, there are up to 5-dimensional observations for each of those multipath components, namely the time of arrival of the path, the angle of arrival at the user site in azimuth and elevation, and the angle of departure at the base station site also in azimuth and elevation. So this somehow indicates that when you have enough resolvable multipath components, you could use those to localize the user and also figure out the user orientation and also synchronize user to the base station. And in fact, you can show that when there's a line of sight between the base station and the user, it is possible to localize the user with one resolved additional multipath component, even if you do not know what is the incidence point of this multipath component, so you don't have any knowledge of the environment. The argument is even stronger. Suppose the line of sight is blocked between the base station and the user. Then we know that each of the multipath components brings 3 unknowns, right, the positions, but up to 5 observations. So if you have enough multipath components, maybe you can also localize a user. And this turns out to be true. If you have 4 non-line of sight resolved multipath components, single bounds, that they together are sufficient to localize the user, figure out the orientation of the user, and synchronize the base station to the user. These combinations are shown here in the table on the right. The nice thing about multipath exploitation is that you don't need many base stations, right? Conventionally, you need 2 or 4 base stations to localize the user, while with multipath exploitation, you can get away with a single base station. You can combine this with tracking of the user over time, in which case you would map the objects in the environment, right? You localize these walls, you localize these buildings as you track the user, and this is known as SLAM, simultaneous localization and mapping. Now, there are some limitations of this approach. First one is that you cannot count on the multipath to be present. And even if it is present, maybe the geometry of the multipath is not very favorable for positioning. The second limitation is that you're not guaranteed that all the multipath components are single bound. There could be a path going from the base station to a first building, to a second building, and then to the user. And those second or higher order bounces are harder to exploit. And finally, the multipath can also be diffuse, meaning that an object like this wall would give rise to many hundreds of multipath components that are not resolvable, and also the multipath may not be always visible. All of this makes it harder to exploit the multipath in practice. An alternative way to exploit multipath is by creating our own multipath. This can be done by using reconfigurable intelligent surfaces. If we place a reconfigurable intelligent surface on the facade of a building, we can create another controllable multipath. Operation of a reconfigurable intelligent surface, or RIS, is shown on the left. The RIS comprises many small elements spaced lambda over 2 or smaller apart, and a controller. This controller adjusts the phase of each of these elements, which it can create non-natural reflections in arbitrary directions, or refractions. So the RIS acts as a controllable multipath component with a known location orientation. If we now look at the different components of the channel, we have first the uncontrolled multipath, as before, for subcarrier N and time K, comprising several multipath components with angle of arrival, angles of departure, delays, and Dopplers. The controllable multipath is given by a matrix as shown here in this new equation. In this matrix, we have, of course, the Doppler with the phase depending on time. We have the delay of the multipath component from the transmitter to the receiver across the subcarriers here. We have the transmitter steering vector at the base station, which depends on the angle of departure from base station to RIS. And this angle is known because we know the base station and RIS position orientation. Then we have the angle of arrival at the user of the path from the RIS. So this is the steering vector at the user side with an unknown angle of arrival. And this angle of arrival is unknown because we don't know the location of the user nor its orientation. Then we have the time-varying complex gain induced by the RIS, which has a fixed part which is independent of the RIS and then a part related to the RIS. This variable complex gain has 3 components. We have here the RIS steering vector, which takes as argument the angle of arrival at the RIS from the base station, and this angle is known. Then we have the time-varying RIS configuration, which is the phase control of the RIS. This is a diagonal matrix. And finally, we have the RIS steering vector as a function of the angle of departure from the RIS to the user. This angle of departure is unknown because the user location is unknown. So in all, we have a known angle of departure from the base station to the RIS and a known angle of arrival at the RIS from the base station. We have an unknown angle of departure at the RIS to the user and an unknown angle of arrival at the user from the RIS, an unknown delay, and an unknown Doppler. If we estimate all of those unknown parameters, this can provide us sufficient information to localize. And this is what is shown in the table here on the bottom row. For instance, if we do angle-only localization, it turns out with 1 base station and 2 RIS, that is sufficient. For other combinations, 1 single antenna base station and 1 multiple element RIS is sufficient to localize the user. In addition to improving coverage and identifiability, there are also methods to improve the accuracy. The first one is in signal design. When we think about conventional pilots, they are designed in time and frequency, shown here with this colorful figure, as well as in the spatial domain. In particular, the positioning reference signals, they span the entire bandwidth, but with some comb structure to allow different base stations to transmit in parallel. In the spatial domain, the base station could use directional beamforming, which provide angle of departure information at the user side. However, these signals, although they're optimized to have a large bandwidth and span a wide range of angles, they're not optimal when we have some prior information of the user. For instance, if we know the user is in the blue beam, then the other beams may not provide much useful information for localization. To optimize the signal, we can write an abstract optimization problem where we minimize with respect to some design variables, this could be time, frequency, or spatial allocation, a position error bound, which, as you recall from the first presentation, is derived from the Fisher information matrix, considering all possible locations of the user, or all user states, here represented by a variable s. So we want to minimize the worst case position error bound with respect to the design variables in such a way that the location is identifiable. So this means that we allow for some ambiguity, provided these ambiguities fall outside of the range of prior knowledge of the user state. Here are some examples. So first of all, we can do frequency allocation. So we have on the x-axis in figure A all the subcarriers, and in the y-axis the fraction of the power that we allocate. We could do a uniform allocation in blue or a non-uniform allocation in red. We could also do a water filling allocation if we know something about the channel state. The figure on the right shows the corresponding range profile. So that's the IFFT output after working in the frequency domain in the receiver. In the green is the range where we know the user is. So we know the user is between, let's say, 7.5 and 12 meters away. This is the prior knowledge we have. And then we have the range profiles for the uniform allocation in blue and the non-uniform allocation in red. So what we see for the uniform allocation, we have a distinct peak at the desired range, at the true range, and then lower side lobes further away. With the non-uniform allocation, we have a sharper peak but strong side lobes. So this means that when we have prior knowledge, which is the green region for the user, the blue profile is preferred because it doesn't lead to any ambiguity in the green region. On the other hand, if we have more information where the user is, if we know the user is in the red region, then the red profile is preferred because it will provide better ranging performance and the ambiguities fall outside of the red range. So this is one example of this signal design in the frequency domain. We can also design signals in the spatial domain. So if we know more or less where the user is, there are optimized beams that we could use. And for instance, for angle of departure estimation, the optimal beams involve directional precoders, as for instance shown on the picture on the right, in combination with so-called derivative precoders, which have a null towards the user. And the combination of those two precoders generates beams which are most informative for angle of departure estimation. Another method to improve positioning performance is by using carrier phase information. So suppose we have multiple base stations that are perfectly synchronized in time and frequency that are sending downlink signals to a user using orthogonal subcarriers. We now want to localize a user from those downlink transmissions. If we use only the time of arrival estimation, that is a standard TDOA positioning. But let's look in more detail at the received signal. So the observed IQ samples from base station M can be written in this form, where here S is the symbol energy, alpha M is the line of sight complex channel gain, and dm is the steering vector across the subcarriers as a function of the delay, given by this expression here. And now alpha M has an amplitude and a phase. Here I ignore all the non-line of sight components for simplicity. Now both the delay and the phase are related to the geometry. The delay of the line of sight component depends on the distance between the base station and the user over the speed of light, plus the clock bias of the user. Recall that the base stations are perfectly time synchronized, so there's no per base station clock bias, only a user clock bias. Similarly, the phase of the complex channel gain depends on the distance over the wavelength plus a phase bias, again because the user is not phase synchronized to the base stations. Normally in positioning, at least so far, we've considered this phase theta m to be an unknown unrelated to the position. However, we can in this case also exploit the relation between the position and the phase. Note that whenever the user moves away a distance of 1 lambda from the base station, the phase is unchanged. So now, from this observation model, we can estimate distances with respect to the user from the delay and the phase information. So for each base station m, we have a distance from the delay information and a distance from the phase information. The distance that we get is the true distance, and in the case of delay information, we have the clock bias times the speed of light plus some measurement noise. In case of the phase, we have the distance plus the phase bias times lambda over 2 pi plus measurement noise plus an ambiguity. And here Zm is an integer which is multiplied by lambda, because every time the user moves 1 lambda, the phase theta m is unchanged. And we do not know this Zm. If we now look at the quality of these measurements here, so if we look at the variance of the noises, it turns out that the measurement variance of the distance estimates when derived from the delay, they scale with 1 over the bandwidth squared. If we look at the measurements and the measurement error variances from the distance derived from the phase, they scale with 1 over the carrier frequency squared. And of course, the carrier frequency is typically much larger than the bandwidth, which means that the phase estimates provide much more information about distance than the delay estimates. So overall, by having carrier phase positioning, we can have much increased accuracy. It turns out we can also have increased resolution for multipath, but we must deal with the carrier phase ambiguity. Luckily, we can rely on the rich literature from GNSS to solve these ambiguities. The third method to improve accuracy is by doing inference over time. The user is not static, but moves over time according to some dynamic model. Every now and again, we measure the distances, angles, and Dopplers which relate to the user state in a nonlinear fashion. And we can then combine those two equations and put them inside of a standard tracking algorithm which aims to maintain a distribution of the state. So it tries to track the posterior distribution of the user state given all the measurements up to that time. Since the measurements are a nonlinear function of the state, we must rely on filters such as the extended Kalman filter or the particle filter. We can also combine this with multipath exploitation, where the state contains not just the user state, but also the incidence points or the state of objects in the environment. And this is again simultaneous localization and mapping. This problem turns out to be challenging because there's an association problem, meaning that we do not know the association of the measurements at a certain time with respect to previously seen objects in the environment. Luckily, there are powerful methods such as based on random finite set theory or belief propagation that can solve these data association problems. The animation on the right shows an example of when a user moves around the base station and how it maps the different objects in the environment, even in the presence of clutter, and at the same time localizes itself based on the direct signal from the base station as well as the signals from the reflections. So these were 3 ways of improving the accuracy. Let us now, in the final slide, look at an outlook towards 6G. In 6G, there will be a variety of technical enablers that will boost localization and sensing performance, but there are also some challenges. So the enablers that I list here, there are 9 of them, are the following. First of all, there will be a variety of carrier frequencies, including sub-6 GHz, millimeter wave, sub-terahertz, and also the golden band around 7 to 10 GHz. This variety of carrier frequencies is good because the lower frequencies provide good coverage, while the higher frequencies provide a more geometric channel. With this variety of carrier frequencies comes also large aggregate bandwidths, probably on the order of 1 or more gigahertz, which provides very good delay resolution, useful for both localization and sensing. When we go at higher frequencies, the user device will have a large number of antenna elements, just as the base station has now, which will allow us to do 3D orientation estimation. So we go from 3D positioning to 6D pulse estimation. There will be side links, so direct connections between devices, which can be used for relative positioning. There will be distributed self-free massive MIMO with phase coherence between the base stations, which we can use for high-resolution sensing or carrier phase positioning. There will be the integration of sensing, localization, and communication, which means not just using the communication infrastructure for localization and sensing, but also to improve communication by knowing where things are and where objects are in the environment. Seventh enabler relates to the use of machine learning and artificial intelligence to provide data-driven solutions to some of the hardest problems in communication system design. The eighth enabler relates to reconfigurable intelligent surfaces, which can shape the environment to overcome, for instance, non-line of sight blockage for communication, but can also improve localization and sensing. And finally, there is the aspect of non-terrestrial networks comprising both LEO satellites and UAVs to complement terrestrial base stations and further provide more coverage and more accuracy for positioning and possibly also for sensing. These enablers, they don't come for free, and I want to highlight two important challenges. The first one is hardware impairments, which, as we have seen, are likely to be much more severe for localization and sensing than for communication. And the last challenge is that when we want extreme performance, for instance, 1 centimeter level accuracy, we need extreme calibration of the devices. We need to know where things are and how they're oriented with a much higher degree of accuracy than before. To use all of these enablers and address the challenges, there's a large number of projects happening right now because localization and sensing will be one of the key defining features of 6G.